It's an example which I called one vector case. I mean, the definition of linear dependence and independence, it is given in the context of n vectors, right? Often when we talk of n vectors, we think of many vectors. But in fact, it also applies equally well for a very simple case of one vector. And let's just see what simpler interpretation we can give for linear dependence independence in case of one vector. Here's my set of one vector. This set can be either linear dependent or linear independent. But in terms of one vector, there are simpler ways to say that or simpler ways to test that, and here they are. Look at this. If my vector accidentally is 0, right? I never excluded 0 from consideration. So if my set consists of one vector and that vector happens to be 0, then I can point out to this relation, which is a trivial correct relation, right? I mean, if you multiply 1 by 0 vector, the result will be a 0 vector. You cannot argue with this. I hope you cannot argue with this. But if you look at this relation from the point of view of our definition, the left-hand side is what I called before linear combination, right? I took my vectors. I say plural, but it's only one vector. It still applies in math. I mean, you can reference single object with plurals in math. It's fine. I took my vectors, multiplied with some coefficients, which I chose, and add them together. And the result ended up to be 0 vector. This means that my set is linear dependent. And this is the manifestation of linear dependence in case of one vector. A set of one vector is linear dependent when it's just a 0 vector. And that's the second part of my argument, if you assume your vector is not 0, then this fact, I hope this fact is known to you. If you have a product over some coefficient and a vector, and it turns out that the product is 0, and you know that one of the factors is non-zero, the only option you have is that the coefficient must be 0. You cannot have non-zero scaling of non-zero vector equal to 0. And that's exactly the implication I showed you at the very bottom of the linear independence definition, which means the set is linear independent. These two lines, this is the proof of the following statement. A set of one vector is linear dependent if and only if when the set is of 0 vector. It's a statement, it's like a theorem, which you see right now on this slide. I didn't frame this as a theorem, but I said it into the mic. You can listen to it again when you watch this video. And these two lines, it's the official, careful, and formal proof of that theorem. A set of one vector is linear dependent if and only if and only if, its equivalence, when the set consists of a 0 vector.